Hello students, today we are going to discuss diffraction. We already discussed interference. Have you seen the geometrical shadow of any opaque object? If you observe the geometrical shadow, you can see, like interference, there also some alternate dark and bright bands. This is due to diffraction. Have you seen different colors on CD? This is also due to diffraction. Now, in detail, we will see what is diffraction. See, here AB is the obstacle and light source is kept here. If we keep a screen here, we will expect shadow in the region A dash B dash and this region perfect light. But we can see that some light it is encroaching into the geometrical shadow. That the encroachment of light into the geometrical shadow, that is called diffraction. Here the same way. Here this was the aperture. Then we will expect complete illumination this region, CD region, and but what we are getting in the region CD near to this here and here the light is encroaching. That means here also the encroachment of light is there. So what is diffraction? Diffraction is the bending of light around the edge of the obstacle or encroachment of light into the geometrical shadow. So, what is the definition of diffraction of light? The phenomena of bending of light around the corners of an obstacle or an aperture into the region of geometrical shadow of obstacle is called diffraction of light. Now, what are the different types of diffraction of light? Mainly, there are two types of diffraction: Fresnel diffraction and Fraunhofer diffraction. In Fresnel diffraction, the source and the screen are at a finite distance from the aperture. See here, in this type of diffraction, the source or the screen or both are at finite distance from the obstacle or aperture, causing the diffraction of light. See this one. Then another one, Fraunhofer diffraction. Here the source or the screen or both are at an infinite distance from the aperture. See here, in Fraunhofer diffraction, the source and the screen are at an infinite distance from the obstacle or the aperture, causing the diffraction of light. In this case, the light from the source is at infinity. After diffraction is focused on the screen using a convex lens. This phenomena of diffraction obtained on the screen is called Fraunhofer diffraction. Here we are going to discuss diffraction of light due to a single slit. In interference, we discussed double slit experiment, Young's double slit experiment. Here we are going to see diffraction of light due to a single slit. What is the experimental arrangement? See here. S is the source of light. It is placed at the focus of the convex lens L1. That means the light coming after refraction from the lens is parallel, and the light is coming parallel. That means the wavefront is a plane wavefront. Then this plane wavefront incident on the slit AB. Then a screen is placed at a distance D from the plane of the slit. Another lens L2 is placed here. The screen is placed at the focus of the lens L2. That means the rays are coming through the lens L2. After diffraction, it converges on the screen. This is the arrangement. See, here we have only one slit, that is single slit. We don't have so many sources. But each and every point on this slit, that is each and every point on this wavefront, acts as the source of secondary wavelets, and it sends out wavelets in the forward direction. At the point O, that is the center of the screen, all the wavelets reaches in phase. So the point O corresponds to central maximum. There is no path difference between the waves coming from the point AC and BC to reach the point O. So O corresponds to central maximum. Say the schematic diagram. The CAB is the slit. Here we divide the slit into two equal halves. See here, this is the first half and this is the second half. The wavelets from the first half and the second half interfere constructively at the point O. So O corresponds to central maximum. Now let the light be diffracted through an angle theta. Then the wavelets also diffracted through an angle theta. So the secondary wavelets converges at the point P. The point P is maximum or minimum depending upon the path difference between the wavelets from the corresponding points AC and BC. Next we have to find out what is the condition for PBA maximum point or PB minimum point. The secondary wavelets diffracted through an angle theta converges at the point P. So what will be at P, maxima or minimum? For that we have to see what is the path difference between the waves from this portion and this portion to reach the point P. So what is the path difference? Here the path difference is Bn. We have to find out how much is the path difference Bn. From the triangle ANB, we can see that sin theta is equal to Bn by AB. Bn is the path difference, so Bn is equal to AB sin theta. AB is the slit width, that is D, so path difference is equal to D sin theta. If we take path difference, Bn is equal to lambda, that is lambda is equal to D sin theta. Theta is very small, so sin theta tends to theta, that is lambda is equal to D into theta. Theta is equal to lambda by D. Now here the interference occurs when more than one source is there. Here we have a single slit, so we divide the slit into two equal halves, each half width D by 2. This is the first half and this is the second half. Then each part of this first half and second half sends out wavelets. These wavelets interfere each other. Then what is the path difference between the wavelets from the corresponding points of the first half AC and the second half CB? That is Cn, that is D by 2 sin theta. D by 2 into theta, that is D by 2 into lambda by D, that is coming lambda by 2. That means the path difference between the waves from the first half and the second half, that means the path difference between the waves from the corresponding point of the first half and second half is lambda by 2. That means phase difference is pi. That means these two waves are out of phase, So they interfere destructively. So the point P corresponds to a minimum point. The path difference is lambda by 2, then the phase difference is pi. That means the waves from the corresponding points of first half and second half interfere destructively at the point P. Why? Because the phase difference is pi. They are out of phase. They interfere destructively. So P corresponds to diffraction minima. Condition for first diffraction minima is d into theta is equal to lambda. Next, if we take d into theta is equal to 2 lambda, then theta is equal to 2 lambda by d. That means we divide the slit into 4 equal halves, each half width d by 4. The waves from the first half, second half interfere. Then the waves from second and third interfere. Third and fourth interfere. So any two we can take. Here we are taking the path difference between the waves from the first half and the second half. Here you will get it is d by 4 into theta. That is d by 4 into 2 lambda by d. That is coming lambda by 2. Again we can see the waves interfere destructively. See the phase difference between these two waves, it is pi. So the waves interfere destructively. That means when you take d theta is equal to lambda, d theta is equal to 2 lambda, both the cases the waves are interfering destructively and we got diffraction minima. So d theta is equal to 2 lambda is the condition for second secondary minima, second diffraction minima. So generally we can say that the condition for diffraction minima, condition for nth diffraction minima is theta n is equal to n lambda by d. N is equal to 1, 2, 3 to infinity. Now if we take theta is equal to 3 lambda by 2d, then we divide the slit into 3 equal parts. Then what is the path difference between the waves from the first part and the second part, and what is the path difference between the waves from the first and third parts we will see. The path difference between the waves from the first and second region, that is coming d by 3 into theta, that is d by 3 into 3 lambda by 2, that is coming lambda by 2. So here the path difference is coming lambda by 2, that means phase difference is pi. So the waves from this first and second region interfere destructively. Now we will see what is the path difference between the waves from the corresponding points of first and third region. So this path difference, how much it is. Here the path difference is equal to 2d by 3 into theta, that is 2d by 3 into 3 lambda by 2d, that is lambda. Here the path difference is lambda, that means phase difference is 2 pi. The waves interfere constructively. So the waves from first and second region interfere destructively and first and third region interfere constructively. So the point P corresponds to first diffraction maxima, first secondary maxima. If we take d theta is equal to 5 lambda by 2, here we divide the slit into 5 equal halves. Here also we can say that the wavelets from some of the parts interfere constructively, some of the parts interfere destructively. So d into theta is equal to 5 lambda by 2 is the condition for secondary maxima. Generally, we can say that the condition for secondary maxima is theta n is equal to 2n plus 1 into lambda by 2d. Next, what is the width of the central maximum? The position of the secondary minima is here, and on both sides the secondary minima is there. That means the distance between two consecutive secondary minima, that is the width of the central maximum. That means here 2 theta, this is theta and this one is also coming theta. So here this 2 theta, see here this is the central maximum, here the width central maximum, and this is the first minimum and this is also minimum. So the width of the central maximum is 2 theta, that is 2 lambda by d. That is the angular width. Then linear width is 2 into x by d, that is equal to 2 lambda by d. 2x is equal to 2 lambda d by d. D is the distance between the plane of the slit and the screen. Here we can see that the central maxima is more brighter than the secondary maxima. When we discuss secondary maxima, we have seen that there few wavelets interfere constructively and few are interfere destructively. So the net effect is the sum of the constructive interference and destructive interference. Because of that, the secondary maxima is less brighter than the central maxima. See here in this graph, it is showing the intensity versus the path difference or phase difference. You can see that width of the central maximum is double of the other secondary maximum, and intensity of the central maximum is more than that of the other maximum. Here the explanation is given why intensity of secondary maximum decreases with the order of maximum. Now, what is the difference between diffraction and interference? In diffraction occurs due to superposition of secondary wavelets. Here two separate sources are there. The waves from the two separate sources interfere. Here not same for all the fringe, intensity is not same for all the fringes. In the case of interference, intensity is same for all the fringes. Width of all the fringes are not same in diffraction. In interference, width of all the fringes are same. Then fringe spacing is non-uniform in diffraction. Here it is uniform. Then intensity versus the wavelength for diffraction and intensity versus wavelength of interference. This is the graphical representation. Distribution of intensity in diffraction and in interference.